All right, let's get started for today. Your homework 5 has been released earlier this week. It's due on Monday. Your project 3 has been released too. That will be due next week, Friday. The project 2 contest results have been calculated. We'll announce those after the break today in lecture. And then the biggest thing coming up is your midterm 1. Midterm 1 is on Monday, March 9th, 6 to 9 p.m. There are multiple rooms. Depending on which last name you have, you'll be in a different room. There is a midterm 1 preparation page up on edX, which has a lot of information about the midterm, including what topics are covered, which is lecture 1 through 11, including all the corresponding homework, sections, and projects. There are past exams on there. I think about 15 or so past exams. There are some special midterm 1 office hours. Take advantage of them if you're not sure about how certain concepts work. There's also a practice midterm. What does that mean? It means that we have a PDF on there that is like a midterm, but it's not going to be your actual midterm. The idea here is that you download the practice midterm, work through it for 3 hours on your own to simulate for yourself what it would be like to take an exam with your current knowledge, whatever that might be at the time you try, of the 188 materials. After you're done working through it for 3 hours, we encourage you to discuss with your friends, other students in class, and so forth about what you found as your answers. You get to submit what you did. It's optional, but you can submit it. And if you submit it, you get 1 point of extra credit on your midterm for submitting it. The condition for submitting is that you spend 3 hours on trying to solve that practice midterm. Hopefully those 3 hours doesn't mean it's still completely empty after 3 hours. If that's the case, we might come and ask you how come your midterm was completely empty after 3 hours. But the bottom line is you're supposed to spend 3 hours, or if you can solve it more quickly and you're done in an hour, then that's fine too, of course. This is due on Saturday, the Saturday when the midterm will be on Monday. The idea here is that if on Saturday night you realize you didn't solve much of that practice midterm, you still have all of Sunday and all of Monday until 6 o'clock at least to continue to prepare for the midterm. Any questions about logistics? All right, so let's look at some AI in the news. So some of you might have seen this yesterday. There was an article published in Nature that was covered by many news outlets about actually reinforcement learning. So what was this about? This is a company called DeepMind, located in London, acquired by Google about a year ago for $600 million. And what they built is a reinforcement learning agent that can learn to play Atari games. Well, let's take a look at what's underneath. What did they do? Well, they actually implemented Q-learning, which we know how it works, but there were a few tweaks to what we see in lecture here that they added to it. So one tweak is that because the Q-learning updates are so fast compared to simulating a step in one of the games, they actually log all their experience that's accumulated and also do Q-learning updates based on logged experiences from the past. So rather than when you experience something, just do an update once to your Q function, keep it around, and reuse it later to do more Q updates based on that past experience. The other thing they did is they actually set up something where the number of parameters is really, really, really high. So it was a parameterized representation, just like we've looked at, so to be able to generalize. But the number of parameters they learn is tens of thousands, or maybe even hundreds of thousands for some, which is a lot larger than what we're looking at in this class. The reason they had this many parameters is because actually what they did is they decided to try to learn directly from a very simple state representation, namely the pixels on the screen. which we all know is a very naive state representation. If you look at the game of Pac-Man, the number of pixels on the screen, the dimensionality of a state space is going to be very high. Same for these Atari games. It's not because they think it's the ideal representation, it's because for a lot of problems in the real world, you might not have access to the full state. The best you might have is a camera, and the equivalent in a video game would be that the best that you have available to you is the pixels on the screen. You don't get that additional information. And so the breakthrough result here was that this was the first result where people showed that you can run reinforcement learning with as input to your, it's called DQN, their Q-learning algorithm, as input to DQN, the pixels on the screen, rather than the underlying state representation, and it can still learn how to play. Now it takes more trials and so forth because it actually needs to learn effectively computer vision along the way to be able to learn to play, but it actually worked, and it's very, very impressive. So I recommend you check it out to get a feel for what some of the most advanced reinforcement learning results are that are currently being achieved. Any questions about this? Yes?
Yeah, so do they use approximate Q-learning, or do they just use Q-learning directly?
So they use approximate Q-learning, so they have a parameterized representation of their Q function. Otherwise, the state space would be, if the state space expressed in terms of pixels, is going to be far too high, especially because the pixels are a continuous value, not continuous, but it goes from 0 to 255 for R, 0 to 255 for G, 0 to 255 for B. So if you naively consider every possible states, just each pixel can already take on 256 to the power 3 different values. So you need some kind of parameterization to get this to work.
Okay. And what kind of parameters do they use?
The way they set it up, and we might see this in one of the last lectures when we've seen more background on that kind of topic, they set it up as a multi-layer neural net. So it's a nonlinear function approximator where the weights of the connections in the neural net are what's being learned. All right, so let's take a look at where we are at in 188. We're done with part 1 out of 3 parts in the course. Part 1 was search and planning. Right now we're starting with part 2, which is probabilistic reasoning. Actually, if we think back to the very first lecture, we had a little history of AI there where we looked at how AI started in the 50s and so forth and kind of hit a little bit of a winter in the 70s, 80s. A big part of that was that there wasn't a good formalism at the time to deal with uncertainty. Probability, of course, is a way to deal with uncertainty, but at the time, the computational mechanisms didn't exist to do these probabilistic computations that you need to deal with uncertainty when there's uncertainty about a lot of different things that you're considering. And so we'll start looking at in this part 2 is how to do probabilistic reasoning. Today, what we'll look at is essentially a math lecture, just a review of probability. And in some sense, today we'll cover everything in terms of what we'll look at it for probabilistic reasoning, but it's only our first pass. We'll see all the concepts, and you'll be able to do everything you might want to do, but only in a very naive way that for practical problems will be far too slow. And then in the 4 lectures, 5 lectures after this, we'll start looking at if we have lots and lots of random variables, how can we still do the calculations we're covering today, but do them efficiently despite the fact that there are lots and lots of random variables. The types of applications we'll be able to solve are problems in medical diagnosis, speech recognition, tracking of objects, mapping. There are also problems where a robot would simultaneously localize itself in a building it's never been in and map out the building. Genetics, where you might infer things about genes based on the phenotypes, error correcting codes, and many, many more. Essentially anything where there's lots of variables that have some randomness to them and that interact with each other, those are the kind of problems we'll be able to solve. Now, then in part 3, what we'll look at is, well, now that we know how to reason with lots of random variables, how do we get the probabilistic models that underlie our reasoning, and how do we build those from data? And that'll be the machine learning part. Okay, so today is all about probability. The concepts we'll look at are random variables, joint and marginal distributions, conditional distributions, the product rule, the chain rule, Bayes rule, inference, which means doing computations with probability distributions and independence, maybe if we get to it, most likely next lecture. The key thing to keep in mind here is that this will be the key concepts for the next 5 to 6 lectures, and you really want to know this inside out. You don't want to have to look things up. If I say, oh, well, we applied a product rule here, you say, oh, product rule, that was in that lecture 12. Let me go look at the slides, what that is again, rethink through it. You're not going to be able to keep up in the next lectures because we'll assume that product rule to you will be like 1 + 1 = 2 to everybody else, so to say. So keep that in mind, that it's not enough to say, oh, I've heard of this, but you actually want to really know this very, very well. So let's look at a motivating example first. So let's look at Ghostbusters. Okay, what do we have here? It's a Pac-Man grid world again. Actually, Pac-Man is not running around in the world now. There is only a ghost. But we don't know where the ghost is. It's in one of those squares. It's not going to move. We know it will stay put in one of the squares. We have a bust action available. If we select that, then we can pick any of the squares. Hit our gun, so to say. If we hit the ghost, we're good, we win. If we don't hit the ghost, that's it, the game is over and we lost. The other action we have available, and which we can take multiple times, is a sensing action. And so we can decide to sense anywhere in this grid. What does it mean to sense? When we pick a grid square to sense, it will light up in a color. It could be yellow, orange, red, depending on how close to the ghost you are. Red is likely when you're very close to the ghost. Orange is likely when you're medium far from the ghost. Yellow when you're fairly far away from the ghost. Could even be green if you're very far away from the ghost. But these sensors are noisy. So even when we see something pop up as red, that doesn't mean the ghost is guaranteed to be nearby. There's a chance that the ghost is far away. And so let's take a look at how this might play out. We're looking for the ghost, so let's try here first. Green. Probably the ghost is pretty far away from here, so let's try to sense somewhere else. Orange, that's likely closer to the ghost. This too. This is apparently likely far away, so maybe somewhere here. That's likely pretty close, but doesn't mean the ghost is necessarily there. We can sense some more to get more evidence in terms of where the ghost might be. All right, so we'll look at this. I think we have a lot of evidence that the ghost is likely somewhere out here. Maybe the red square, but maybe not because it's green right next to it. Who knows? We have to make a decision. Let's pick something. Let's go for the red one because that seems most promising. And we got the ghost, we win. Now this was pretty heuristic what I did here. I didn't actually know that that was the most likely square, and part of what we'll look at today is see how we can associate numbers with each of those squares that tell us how likely it is that the ghost is in that particular square after the sensor measurements we made. So to make this more concrete, what you would have is you would have a probabilistic model, and that model encodes how your sensors work. So for example, given the distance from the ghost is 3 for this table here, there's a 0.05 probability that the sensor measurement will be red, a 0.15 probability that the sensor measurement will be orange, 0.5 probability for yellow, and 0.3 probability for green. There's a similar table for when the distance to the ghost is 2, when it's 1, when it's 0, when it's 4, 5, 6, and so forth. So we have a set of tables for each possible distance, one table encoding how the sensor will work, in this case in a noisy way. What's important to realize here is that this table goes from what you can think of as cause, namely the distance to the ghost, to the effect. Right? The sensor measures some consequence of the ghost being somewhat nearby. What we're really interested in usually is the other way around. We're interested in, if I measure green, how far away is the ghost? But this number is not telling us when we measure green how far is the ghost most likely. That's not what it says. It's saying if the ghost is 3 away, then the probability of measuring green is 0.3. You might ask, why don't we have the other table that we might be more interested in? Because that table is usually not available to us. Usually when you have a sensor, the way it works is that there's some physical underlying process, and for a given current real-world situation, there's a distribution over outcomes. But there's no process the other way around that says, if you measure this, then physically this is what you would likely have in the real world. And so we'll learn how to manipulate a table that's given to us in this format into something that's the other way around, which we'll want to decide where the ghosts actually are. Okay, so the thing we're dealing with here is uncertainty. The way we'll deal with uncertainty is by having variables. There are 2 types of variables. Observed variables are the ones that we get to see. For example, once we made a sensory measurement in a certain square, that is an observed variable. Unobserved variables are the ones we typically care about more. Because if all we cared about the observed ones, we would not even worry about the unobserved ones, take them out of our process of what we're thinking about. So usually we care about the unobserved ones most, and often we don't even have a chance to observe them. All we get is other ones that somehow relate to them. The way the unobserved and the observed variables relate to each other is specified in a model, and that model will be used to make inferences about the unobserved ones based on what you observed. All right, so random variables. Here are some examples of random variables that tend to represent things about the world that are uncertain. R, capital R, is it raining? Values could be true or false. Is it hot or cold? How long will it take to drive to work? Where is the ghost? Which could be a discrete variable or a continuous variable, depending on how you define your problem. We'll always denote random variables with capital letters, as shown here on the left. Now this is a lot like what we saw in CSPs. We could have as a CSP variable, whether it's raining or not, the domain is true, false. Often we might have shorthand notation plus R, negative R, and so forth. But so what's going on here is that we have a similar setup to what we had for CSPs, variables and domains. But the difference is that in CSPs, we don't have any uncertainty in the sense that we have it here. They are just looking for an assignment that's compatible with our constraints. Here, our probability is going to be associated with each possible outcome. What this thing here means specifically, plus R, is shorthand for the random variable capital R takes on the value true. The nice thing about the shorthand is that much shorter to write, and if you use the more naive shorthand like just true, then you don't know anymore what random variable you're talking about. Okay, so those are random variables. We'll care about distributions over them. So let's look at temperature. There are 2 possible values, hot or cold. We could have equal probability for each one of them. This would be our probability distribution. Weather, maybe there are 4 possible outcomes. It could be sunny, rainy, foggy, or there could be a meteor shower. And the second column here gives the probabilities of each of those outcomes. Keep in mind that for now you're given those tables. You could argue with those. You could say, well, I think 0.6 is not the right number. That's fine. That's really important in real life that you get those numbers as accurate as possible. But for the things we cover in the next few lectures, it actually doesn't matter where you get those numbers from. They're given to you, and we'll learn to work with them. Okay, so distribution is essentially a table, right? The first column indexes into the values in the domain. The second column gives associated probabilities. If we look at things we can read off, the probability of W equals rain equals 0.1. What must be satisfied by these tables? 2 properties. First one is that every entry has to be bigger than or equal to 0. Otherwise, it's not a valid probability distribution. Second property, the sum of all entries has to be equal to 1. Once those two properties are satisfied, everything else you can freely choose, which means for this table here with 4 possible values, there are, in pretty much any probability table, there will be infinitely many choices for those numbers. You happen to just encounter one specific distribution here. Some notation. The full notation would be this: probability of temperature equal hot. A shorthand that we use quite often would be P hot. What that means here is that this thing on the left is really the same as the thing on the right. Whenever the domains of the random variables are such that they don't share any values, the thing on the left is unambiguous and you can use it. Now, if all your domains are true, false, and you write P true, then it doesn't make sense. But in this case, if there is no repeat values in domains, you can use this kind of shorthand. What will be interesting to us is joint distributions, because that's how we'll be able to make inferences about one variable given information about other variables. So joint distribution over a set of random variables specifies a real number for every possible full instantiation. So if we had n random variables, x1 through xn, this here is a probability of a full instantiation. The row below is a shorthand notation for the first row. Here's an example of a joint distribution. The initial columns will be indexing into the random variables, and in the last column will be probabilities again. And now we have an entry in this table for every possible combination of values these random variables can take on. So in this case, 2 random variables each can take on 2 values, so we have 2 times 2 entries in the table. Properties they have to satisfy, just like for a regular distribution, joint distributions need to have all entries positive and need to have their entries summed to 1. Once that's satisfied, it's a joint distribution. Right. What's the size of a joint distribution over n variables with domain sizes d? I hear d squared. I hear d to the n. Okay, let's think about this. What is the total domain size? What do you get to do? You get to pick, you need to look at all possible joint instantiations. So you can pick any instantiation for your first variable, that's d choices. And for any choice you make there, you get d choices for the next one. Any choices you made before, you again get d choices for the next one. And this keeps going till the very last one. You have n times that you get to pick. So this is equal to d to the n. And this is not unlike what we saw in constraint satisfaction problems. If we had n variables with domain sizes d, the bottom of that search tree had d to the n leaves. Same thing over here. It grows exponentially with the number of variables. So once there's a lot of variables, representing this kind of table will be impractical. And we'll need to look at different techniques to encode probability distributions that don't involve specifying this full table in those scenarios. That's what we'll essentially be working with in the next 5 lectures. Okay, so what is a probabilistic model? A probabilistic model is essentially just a joint distribution over a set of random variables. Each random variable will have a domain, assignments, we will call outcomes, what could happen to that random variable once it's known what its value is. Joint distributions encode which assignments are likely and less likely. They sum to 1, and often you set it up in a way that only small sets of variables interact with each other directly. Just like we saw for constraint satisfaction problems, where we had a constraint satisfaction graph encoding the constraints between variables, and often the graph would be sparse with only a small number of connections rather than every variable being connected to every other variable in the graph. We'll do similar things here. So the analogy is very, very strong. CSPs also have variables with domains. There are constraints there, which is slightly different than probabilities, but it's quite related. It's in some sense saying what is possible, not possible, as opposed to what's more or less likely. And then ideally, also in CSPs, only small subsets of variables interact directly. Okay, what's an event? An event is a set of possible outcomes. So an event E is a set of joint instantiations of the random variables x1 through xn. And the probability of an event is then the sum of the probabilities of those joint instantiations that constitute the event. From a full joint distribution, we can compute the probability of any event. We specify an event, which is a set of instantiations. You can sum together the probabilities of those instantiations and get the probability of that event. So let's look at some examples. What is the probability of the event hot and sunny? Well, let's see. Here's the joint distribution. Hot and sunny is only happening in this line over here, so the answer is 0.4. What's the probability that it's hot? Well, which joint instantiations correspond to hot? Hot is over here, so these two rows, 0.4 plus 0.1, which is 0.5. What is the probability that it's hot or sunny? So that means rows with hot will be included, rows with sunny will be included. So we have the first row, second row, third row. We sum those together, we have 0.7. Note that we don't double count the first row just because it's both hot and sunny. We just look at every row that's compatible with the event and sum the probabilities together. All right. Typically what we'll care about in terms of events will be events of the type, what's the probability that a t equals hot, or if you have many random variables that some small subset of variables take on a certain set of values. So let's do another example here. Here's a new joint distribution, and let's see if we can figure out the probability of each of these events. First one, plus x plus y. Hearing 0.2. Why? Because this is the only row that has plus x plus y, and it has 0.2. Plus x. Hearing 0.5. Y. Plus x is here. These two rows sum up to 0.5. Then minus y or plus x. I'm hearing 0.6. Let's see. Negative y is here and here. Plus x is here and here. That's 0.2 plus 0.3 plus 0.1, which is 0.6, which keeps disappearing. There we go. Okay, next concept, marginal distributions. Marginal distributions are effectively subtables of our original joint distribution that we get from eliminating certain variables by summing them out. So here is the joint distribution we're starting with in this example. Let's say we're interested in the marginal distribution for t. That means is we're interested in a table that just has the random variable t in it, which can take on the values hot or cold, and then we want the corresponding probabilities. So this is what we would get. We know how to compute this. These are just two events for which we compute the probability. Here's the particular equation, but we really already solved this type of problem on the previous two slides. You will want to familiarize yourself, though, with how this is written out here. What is this saying? It's saying that to compute the probability of a particular instantiation, small t could be hot or cold. It's not specified. It's just small t means that we instantiated the variable capital T to something, is equal to, and then we look at the joint distribution. We take the entries where we have the value t, small t for temperature, and then sum out over all possible values the other variable can take on. Okay, we can do the same thing for weather. If we want the marginal distribution for weather, this is a table that will have two entries, one for sunny, one for rainy. We know how to do that. We can compute the probabilities of both of these events, but again, the notation here is something you need to become very familiar with. We have a probability for some instantiation S for weather is the sum over all entries in the joint distribution where W equals S and the other variable can take on all possible values, and we sum over all possible values. Generally, what it looks like is like this. Over here, if we have a joint distribution over x1 and x2, we want the marginal over x1 to compute an entry for that marginal. We look at all entries in the joint that are compatible with x1 equals x1, but sum out over all possible instantiations of, in general, all the other variables. In this case, just the one other variable that exists. Okay, let's do a quick quiz on this. Here is a joint distribution. We're interested in the marginal over x. What will it look like? Well, this is the type of calculation we do. Plus x, well, sum over all rows where we have plus x, independent of what value y takes on, which is the first two rows, so we have 0.5. And then we can take a shortcut for the second one. We actually know that this table has to sum to 1. It's a probability distribution, so without even looking at the original table, we know this will also be 0.5. Marginal for y. What's the marginal probability for plus y? We sum over all possible values x can take on while we keep y fixed to the entry we're interested in. Plus y is sitting here and here, so that sums to 0.6. Then for negative y, we know what's left is 0.4, and we can fill that in too. All right, we've seen marginals. Now let's take a look at conditional probabilities, which will actually be the main thing we'll be working with a lot. What's a conditional probability? What we look at here is what's the probability of some event A given that we know an event B is true. So that's what this is saying here. What's the probability of A given B? This here is a definition. You can't prove this. Not the way we're covering probability, at least because we're defining conditional probability to be exactly what's shown over here. Is the probability of A and B happening divided by the probability of B happening. Pictorially, you can think of this rectangle as a boundary around every possible thing that could ever happen in the world. And every point in that rectangle encodes something in terms of this is what the entire world could be like. Now, A is a particular event that you might care about, maybe that it's raining or something. B is a particular event you might care about, whether it's maybe hot or cold. Then some part of all possible worlds has rain, some part of all possible worlds has hot, and then there's an intersection here shown in the middle where it's both, let's say, raining and hot if A is rain and B is hot, and everything that's left white has A false and B false. Everything that's in the blue area here has A true but B false, and then everything in the red area here has B true but A false. All right, so pictorially what's happening here is that you're computing the area taken up by this intersection here and dividing it by the total area taken up by the event B. And that's saying the fraction of the time that A and B are true when we already know we're in the set where B is true. Okay, so let's look at the joint distribution as a starting point. Two random variables, T and W. And let's look at a conditional probability calculation. So we're interested in the conditional probability of it being sunny given the temperature is cold. Well, how do we compute this? The definition is right here. We need to look at the probability of W equal S and T equals C divided by the probability of T equals C, which is equal to the first one, S and C is over here. We can just read it off, 0.2. The second one, probability T equals C, that's an event. That's not directly in the table, but we know how to compute that probability. We just have to sum over all entries in the table that have T equals C, which is the last two rows, which sum to 0.5. And so this is our conditional probability. It's a 0.4 probability of sunny given it's cold. Let's put this in typeset. So here's the full calculation that we just did. All right, let's try a few more. Well, I'll give you a little bit of time to think about it and shout out the potential answer. So what is the probability of plus x given plus y? Any thoughts? I'm hearing some 1/3. Any other suggestions? Okay, so how do we get there? Plus x given plus y is the probability of both plus x and plus y being true divided by the probability of plus y. Keep in mind the one at the bottom here is always the one in the back there. And plus x plus y is 0.2. And plus y appears here and here. That sums to 0.6, so we have 1/3. How about negative x given plus y? I'm hearing 2/3. That was pretty quick. How do we get there so quickly? Well, we know that x can only take on 2 values. We already know the probability of plus x given plus y. So the probability of negative x given plus y is going to be the complementary thing to make sure it is summed to 1. So since this is 1/3, this one will be 2/3. How about negative y given plus x? I'm hearing 3/5. How do we get there? It's probability of negative y and plus x divided by the probability of plus x. Negative y plus x is over here, 0.3. Plus x is the first 2 rows, which is 0.5. So this is equal to 0.6. Okay, so these are individual conditional probabilities. You're given one specific query here. What's the probability of plus x given plus y? Another specific query, and so forth. What we can now start looking at is conditional distributions. What that means is we look at an entire set of conditional probabilities that somehow belong together in one table or a combination of tables. So here's a conditional distribution. The distribution for weather given temperature equal hot is a distribution where we have only one variable that remains, weather, because temperature equals hot has been fixed. It's not a variable anymore at this point. So we have just the weather variable here, and then we have probabilities in the second column. They sum to 1 because it's a distribution. Now we can do the same thing for temperature equals cold. And so together, we write this as this thing over here, P capital W given capital T. That denotes the set of conditional distributions shown over here. In general, something like this will denote a set of conditional distributions where we have one table for each possible outcome of the variables that are behind the conditioning bar. This vertical bar here is the conditioning bar, and we'll have one table for each possible outcome of the variables behind it. All right, so that's conditional distributions. Now we'll see a little trick to compute those conditional distributions from a joint distribution. Keep in mind, we already know how to do this, right? If I gave you this over here, the joint distribution, I asked you to compute the conditional distribution, W given T, you could do this as we did on the previous slides. You could say, well, I need to compute 4 entries total. Let's compute 1 entry at a time, fill them in, and be done with it. But there is a slightly quicker way to do this, which we'll see often later, and you'll actually implement this in your project 4, which will be a few weeks from now. So this is called the normalization trick. Let's first look at how we can do things naively, and then see what the pattern is, and then from that pattern go to the trick to do it more readily. So if we want to compute one of those conditional distributions, the one for temperature equal cold, we can say, well, that has 2 entries. Let's compute that first entry. It's equal to this expression over here. That's just the definition of conditional probability. Didn't do anything there. The top row is in the table, so we're all set. The bottom row is not in the table, actually. But it's going to be a sum of entries in the table, and we write it out that way. And now we have an expression with only entries that are in the table, so we can calculate it and have a number. We can do the same thing for weather equals rainy. And so step through the same set of steps. Here's what we get. Now, the observation here is that if you look at what we're using from the original table, we're only using entries from the original table where temperature equals cold. Entries where temperature equals hot don't appear in this calculation anywhere. Okay? So that's something we'll rely upon. Another thing to notice is that if you look at this denominator here and this denominator here, they're actually the same. In fact, we know they're going to be the same because it's already the same here, and we just then re-express it in terms of entries we have in the table. Now, effectively what that means, since we know when we get the final table here, things will sum to 1, it means that instead of doing this full calculation every time, we could ignore what's on the bottom, just look at what's on top, just take those numbers. They will not sum to 1 because we know we still have to divide all the numbers that we picked by some fixed number that we still have to calculate. But actually that fixed number, all it does is make sure things sum up to 1. So we can take the numbers that are on top, build a table from those numbers, realize those numbers don't sum to 1 yet, see what they sum to, divide by that, and now they do sum to 1, and we're done, and we did effectively what's already here, but we did it in a slightly more efficient way that's often more convenient to work with. So that's the normalization trick. We have these calculations here. All we do is we select the joint probabilities that match the evidence. In this case, the evidence is temperature equals cold. Here's our new table, where we only kept temperature equal cold rows. These effectively correspond to the top entries here. We know that the denominator will always be the same anyway, so we don't worry about it. We do know that what it does is makes this sum to 1, so let's see what the current sum is. We'll compute the current sum, which is 0.5, divide by it, and we'll get our normalized table. A little bit of notation here. This will come back many times in future lectures. What is this thing over here? This is saying that you had essentially a joint distribution initially, which we had over here. But now, for one of the variables, we instantiated a specific value. It's accordingly lowercase, small c. And so we have a smaller table, only the rows in the original table compatible with temperature equals cold. All right. So in general, what does it look like? You might have a table over 2 variables, x1 and x2, or even more. If you're interested in the conditional for x1 given x2, we know that it's going to be x1 comma x2 and then divided by the probability of x2. This at the bottom here is essentially just summing over all compatible entries with the value that we have for x2. And so this often we'll just call z our normalization constant, and we just compute z separately and then divide everything by z. So let's try this out on a small example. What's the probability of x, where x could take on plus x or negative x, given y equals negative y? Okay, what does the normalization trick do? It says, well, what we need to do is first subselect. So we grab the table x comma negative y, which will have x as a variable, y will be negative y, so it'll be fixed. We can still include it, but it won't really do much. So negative y every time, and then we have x could be positive x or negative x. We have 0.3 and 0.1. We normalize, which means we compute this normalization constant z, which is 0.3 plus 0.1, which is 0.4. Then we divide everything in this column here by z. We end up with, in this case, x, y, p plus x, always negative y. We now have the table for x given negative y, and we divide by z, which is 0.4, so we have 0.75 and 0.25. Okay, why do we call this the normalization trick? Normalizing, what does it mean in general? It means restoring something to its normal condition. What do we mean with normal condition when we are talking about probability distributions? It means we want everything to sum to 1, because that's what a probability distribution is like. Right? So we end up with a table where things didn't sum to 1. Normalizing that table means making everything sum to 1. So you compute z, your normalization constant, as the sum over all entries, divide every entry by z, and you've normalized your table. Here's a first example. We have a table, 2 entries. It's not normalized yet because it sums to 0.5. We compute z as 0.5, divide by it, and we have a normalized table. This can actually also happen when your entries sum to something more than 1. In this case, this sums to 50. Fine. So z is 50 in this case. We divide every entry by 50, and here's our normalized version of that table. All right, let's take a short break here, and let's continue with probability after the break. All right, let's restart and take a look at the Project 2 mini contest. What was the contest here? On one side of the board, you are a ghost. That's your own side. That's the side you get to defend. On the other side, you're Pac-Man. You get to eat the dots. When you eat dots, you don't immediately collect score for it. You actually need to bring them back to your own side to get the points for the dots you collected. All right, let's take a look at the top scoring teams. We have top 10 here. At number 10, we have Jason Lee Jiang with "Maybe I Should Have Gone to Lecture." He's probably not here today. At number 9, we have Nick Xu and Ted Xiao with 1 billion points. Not sure how I feel about that at number 9. Number 8, we have Dalen Yang and Ravi Tadinada with Knife Intensive. At 7, we have Rirong Zhu and Chuxian Li with Win by 5. Then at 6, we have Lydia Li with Intentional. At 5, we have Joshua Mack with That Dirtbot-ish Back. At 4, we have Jonathan Tao and Fabian Ho with Packlemore. Let's congratulate all of these. And we have a top 3 in random order. We have 50 Shades of Pac-Man. We have a Pac-Man. And we have Doji. So 50 Shades of Pac-Man stood 3rd in contest 1, Doji stood 9th, and Pac-Man did not participate in contest 1, but is right here in the top 3 for contest 2. Okay, let's take a look at the strategies. So let's take a look at 50 Shades of Pac-Man. Anthony Su and Pieter Lee. Find the shortest paths to unique dots on the other side. Determine all locations in the game from which we could escape if being chased by one opponent. At any given time in the game, find food dots that we can safely reach and then return to a position in safety set. If we cannot find any such food dots, try to return to own side safety. If this is also not possible, print expletive accept fate, and return random moves. If we are winning, play defense/camp, unless we are scared, in which case see previous. Reflex agent, for Alan Zhao, it's a reflex agent, no planning, that tries to move towards the nearest food capsule, towards the nearest prey, agent it can eat, and away from the nearest predator, with fairly arbitrary weights. Implemented cul-de-sac detection, forcing Pac-Man to retreat from a cul-de-sac if the nearest predator can reach the exit before it can. Very small penalty to encourage the two agents to spread apart. All right, let's take a look at these two facing off. 50 Shades of Pac-Man. Anthony Sue and Pieter Lee. Are Anthony and Pieter here? Let's see. Anthony and Pieter. Is that Anthony or Pieter? Anthony. So Anthony Sue over there. Alan Zhao. Alan here. Over there. Did you raise your hand? All right, Alan there. Let's see how this plays out. 50 Shades of Pac-Man in red on the left, and Pac-Man in blue on the right. Oh. So the winner is Pac-Man, and this puts 50 Shades of Pac-Man in third place. Now we'll look at the remaining two teams. So we have Doji versus Pac-Man. Doji is Kai C and Denise Zito. Are Kai and Denise here? Any hands? Kai and Denise all the way in the back. So it's Kai and Denise all the way in the back against Alan Zhao right there. Okay, choose your allegiances smartly. So this is for first place. Doji on the left. Pac-Man on the right. Here we go. So we have our top three figured out. So we have 3 50 Shades of Pac-Man. Congratulations, Anthony and Pieter. At 2 we have Doji, Kai, and Denise. Congratulations. And at 1 we have Alan. Congratulations. All right. Now, there is one more contest coming up, it's the final contest. Stay tuned for that. That will come out a few weeks, maybe 4 or 5 weeks from now, probably. It's going to be a new final contest, different from what it was previous years. You'll see what it's like. It will be more advanced. There will be base nets in it and so forth. It'll be really, really exciting. So stay tuned for that. Also today is some great evidence that you could not participate in any of the previous contests and still win the next contest. So don't be discouraged if you didn't participate in 1 and 2. Jump right into the last contest and maybe you'll win just like Alan did here. All right, any questions about the first half of lecture? Then let's continue our journey of probability. Hopefully most of it reviewed, just maybe a little bit of new notation to get used to. Probabilistic inference. What does that refer to? We're going to be doing probabilistic inference for much of the remainder of 188. It means that you compute a desired probability from other known probabilities. Why would that ever happen? Because typically the way people will provide you with probabilities, or the probabilities you're able to learn from data once we do machine learning, are not usually the ones you ultimately want to make your decision based on, and you'll need to do some kind of transformation of the representation you had initially to the representation you need to make your decisions. So often there'll be conditional probabilities. Why? Well, that's usually what you're interested in. Conditional probabilities will encode things like, what's the probability of that you're on time given that there are no reported accidents? And something like this will be where we get our beliefs for the agents. Remember, we had things like Expectimax, where an agent looked at distributions. Well, an agent might have received some evidence, done a probabilistic inference computation, and then used the result of that computation to put on the branches in this Expectimax tree. These probabilities tend to change when you get more evidence. So we had a probability of, let's say, 0.9 of being on time when there's no reported accidents. But now if in addition we found out it's 5 a.m., it's even more likely that you'll be on time, because when it's 5 a.m. there's typically less traffic and you go faster. Now if in addition to no accidents and 5 a.m. you find out that it's raining, now the probability goes down again, because with rain usually things slow down, and now only a 0.8 probability anymore to be on time. So new evidence will typically cause the beliefs an agent has to be updated from what they were before. What we'll see now on the next slide is the first general procedure to do probabilistic inference. So let's assume we are given a joint distribution over many random variables, x1 through xn. We're asked to compute a specific conditional probability. Let me show it on the slide. A probability over a query variable q given some evidence variables e1 through ek. So x1 through xn is all variables, but some variables are evidence variables. You get to observe them and you know their values. Some of them are query variables, which are the ones you care about knowing the probability for given the evidence. And then there are other variables that are just sitting there in your joint distribution and that are not in your query and not in your evidence. But they're there because the joint distribution you got had those additional variables. Those we call the hidden variables. Okay, so how do we do inference by enumeration? So given a joint distribution, how do we compute this thing over here? What will that look like, what we're computing here? It'll be a table with one entry for each possible value of q. And e1 through ek will be fixed to whatever values they are. Okay. The first step is to select entries consistent with the evidence. Right? Because we've already seen how to compute conditional probabilities. We know that the only things that contribute from the joint distribution are those rows that are consistent with the evidence. So we get rid of everything that's not consistent with the evidence and just retain a smaller table. Once we have that smaller table, before we just normalized, but now we have those hidden variables which we still need to account for, which we don't want in our table, but which are still sitting there. And so we sum out over our hidden variables to get the joint over query and evidence. What does that look like? It looks like this. We'll have entries in our table that consider query, hidden, and evidence. Evidence in our table is fixed. It's all exactly what we want it to be at this point in this smaller table. The query values, we want to retain everything, but then the hidden variables, h1 through hr, they could take on a variety of values. We know that we don't care what they are, so we sum over their possible instantiations, and we get now a new table that doesn't have them anymore, with one entry for each possible value of q. We'll see some examples on the next slide. Now we have a table pq, e1 through ek. This table is of the type we like, but in general, the entries will not sum to 1. So what do? We normalize, we sum all entries together, call that z, multiply every entry by 1 over z, and we get our answer to our conditional probability query. Okay, so this is very procedural. This is something you could code up. You could say, well, I'm writing a piece of code where I'm giving a joint distribution. Somebody tells me what the evidence variables are, what their values are that I observe, what the query variables are. All the other ones are the hidden variables, and you can execute this procedure. Q here is denoted as one variable. If you had Q being multiple variables, just the same thing will work. You retain all entries consistent with the evidence. You sum out over hidden variables. And when you look at this equation here, what's happening here exactly is important to keep in mind. So let's look at this really closely. What's happening is to compute one entry in this table for PQ, comma E1 through EK, to compute one entry, we fix one value for Q, let's say plus Q. The E variables are already fixed. Then we'll look at all entries that have plus Q and E1 through EK. There will be multiple entries because the hidden variables can take on different values. We sum together all those entries, and that will give us the new entry for plus Q, comma E1 through EK. And then we can repeat this for negative Q, and if there's yet another version of Q, you can repeat this again and so forth. Okay, so let's do this on an example table. So here's our joint distribution, 3 random variables. Our first query is for W. So what are our query variables? Query variable W. Evidence variables, no evidence variables, empty. And hidden variables are S and T. So these are our hidden variables. This is our query variable, and there is no evidence variables. So first step, get rid of everything that's not consistent with our evidence. There is no evidence, so everything is consistent with the no evidence we have, so we keep everything. Next step, we sum out over the hidden variables. So we're going to generate a table now that only contains values for the query variable. So we have a table where we just have W, which can be sunny or rainy. We'll have probabilities. And the way we do is we look at one row at a time here, and we look at all entries in the original table that are consistent with this and consistent with the evidence. So we have sun, 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 and that sums up to 0.65. And then we do the same thing for rain. Rain is here, 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 here. We sum up those entries, which is 0.25, 0.3, 0.35. Then we normalize. In this case, it's actually already normalized, already sums to 1, so the normalization doesn't do anything. And we have the answer to our query. All right, let's look at a more complicated one. W given winter. So in this case, this here is our evidence variable. Then weather is still our query variable, and temperature is our only hidden variable. What's the procedure? Inference by enumeration. First, we only retain things consistent with the evidence. So we get rid of anything that's not consistent. So these rows are gone now. We're just left with the table at the bottom here. Then we sum out over the hidden variables, which means that we're building a table now where we have our query variable as a variable, and we'll have probabilities. Well, they don't need to be probabilities just yet. We might have to normalize. We have numbers there. And then we have, for our query variable, can be sunny or rainy. We compute these one at a time. So first look at sun, which is here and here. We sum both of those entries together, 0.25. Then we do the same thing for rain. That sums to also 0.25. Now we normalize. The normalization constant z is equal, or factor 0.5, which is a sum of 0.25 and 0.25. We divide by z, and we end up with our conditional table with entries of 0.5 and 0.5. All right, let's do a last example. Here we have a query variable. Query variable is W again. Over here. Then we have as our evidence variables winter and hot. So our evidence variables are the season and the temperature. We have no hidden variables because those three together are all variables. All right, so first step, retain only what's consistent with our evidence. That's winter and hot, so that's these two rows here. Next step, sum out over the hidden variables, but there are no hidden variables, so that's a no-op, nothing to be done there. Next step, normalize. Well, what's z here? Z is 0.1 plus 0.05, so it's 0.15. And so ultimately what we end up with is a table with entries 0.1 over 0.15 and 0.05 over 0.15. And that will be, the first one is the probability for sun, the second one for rain. Any questions about inference by enumeration?
Aren't there still hidden variables in this case?
In which sense?
The S and the T aren't, the season and temperature aren't part of the query. Like, why is the hidden variables in the third one different than the first and the second two?
So the way we define hidden variables is really what your question is about, right? How to define what's a hidden variable versus what's something else. So when we're given a probabilistic inference query, the variables before the conditioning bar are the query variables. The ones behind the conditioning bar are the evidence variables. And everything that's not been considered yet are the hidden variables. Now it is true that you don't know what the value of W is here. It's still hidden to you. You don't know the outcome yet. But terminology-wise, we wouldn't call it a hidden variable. We would call it a query variable. Okay, what are some obvious problems here? Well, the worst case time complexity for running inference by enumeration is d to the n. Why? Well, that's the size of the table that you're interacting with. And worst case, you might have to consider every entry in that table, and so it's going to be an expensive computation. Space-wise, same thing. It requires having a, full joint distribution, which, if you have many, many variables, will not be practical. So what we're going to start looking at now is how we can represent distributions over many variables, but without needing a full joint distribution to start out with. So first thing we can do is look at the product rule. What's the product rule? Product rule says that the joint between x and y can be written as the marginal for y multiplied with the conditional of x given y. What that means is that we can specify the joint by never specifying the joint distribution table, but by just providing the two things on the left here. And implicitly that encodes a joint distribution, because you can compute everything in the joint distribution from those two. Why is this true? This is just based on the definition of conditional probability. Conditional probability was defined this way. Now we just bring py to the other side and we get what we had on the left. And so we know this can be derived directly from the definition. So here's an example of how we could use this. Let's say we're interested in a joint over d and w, but we don't want to specify it, or it's hard to find what the joint is because those entries are hard to elicit and say, oh, what exactly is the joint probability between sun and wet or something. You say, well, maybe somebody is able to provide you with a marginal for just weather, a conditional for dry or wet, given weather, and then you can build the full joint using the calculation shown over here for every single entry. So let's do one of them, wet and sun. What do? We look at the marginal for weather. It's sun that we're interested in, so that's 0.8. Then we multiply with the conditional of wet given sun, which is over here, 0.1, and we get 0.08 as our entry there. We can do the same thing for the other three. And this is what we end up with. All right, you can generalize this, and the generalization is really what we'll care about a lot. When you have many, many variables, you can say the joint, in this case between three variables, is expanded this way over here. What is that saying? Joint between x1, x2, x3 is the marginal of x1 times the conditional of x2 given x1 times the conditional of x3 given x1 and x2. You can do this in general this way here. What is this encoding? This sign over here is a lot like the summation sign, except that it's a pi instead of a sigma, which means you're multiplying together terms rather than summing them together. So what this here is really px1 times px2 given x1 times x3 given x1 comma x2 and so forth all the way till xn given x1, x2 through xn minus 1. Why is this always true? Why can you always expand a joint probability as a sequence of conditionals? Well, you can prove this by induction, but effectively what's happening is you're applying the same thing over and over. You can say, well, what's the conditional probability of, in this case, or what's the product rule applied to, let's do it for the first one, x1, x2, x3 is equal to, based on the product rule, and let's think of this as just one big variable, then that's equal to px1 times p x through and x3 given x1, then we can apply the product rule effectively to this thing over here. Things behind the conditioning bar don't affect these kind of rules, so it can then have px1 times p x2 given x1 times x3 given x3 given x1 x2. You can also more formally prove this by induction, where you first show it's true for just x1 and x2, and then you rely on that result to get it for x3 and so forth. Now that we know how to compose distributions, let's take a look at how we will often use this. Bayes' rule is this thing where you start flipping probabilities around. So let's say you have a joint distribution over two variables, x and y. You can use the product rule in two different ways. You can swap the roles of x and y to get those two different expressions. They're both equal to the joint, just swap the roles of x and y. They can use this to get that the conditional for x given y is expressed as a conditional of y given x, and then there's also probability of y and probability of x. That is Bayes' rule. It directly follows from the definition of conditional probability, which implies the product rule, which in turn implies Bayes' rule. Okay, so this is named after Reverend Bayes, who invented this a long time ago. That's his rule. Why is this helpful? Why do you care about doing this? Very often in practice, you will be given y given x, but you'll be interested in x given y. Just the way things tend to play out. So that's why this is really interesting. Okay? This is maybe the most important equation in AI, and that we'll see this come back and back and back and back anytime we deal with probabilities. So here's an example of what you might do. Let's say you're interested in diagnosing some kind of illness. There is a cause, there's an effect. Now, usually what you know is a model that if there's a cause, some kind of illness, there's a probability of it causing some effect. And that's what you know. Then you know the underlying baseline probability of the cause. You know the probability of the effect on average, or you can actually compute it from the other two. And then you can apply Bayes' rule to get this out here. For example, you're interested in the probability of meningitis given some symptom is true. You can use Bayes' rule to re-express it this way. These are the quantities available. The one at the bottom we don't have, but we compute the one at the bottom this way over here. What is that saying? Well, it's the probability of plus s comma plus m and the probability of plus s comma negative m, which we can find with the product rule. And that way we compute the probability of plus m given plus s from these here, which are essentially the reverse. Okay, so this is a typical example, cause and effect. You get a probability one way, you want the other one. Now, thinking back to what we did in the first few lectures, now if you start using those probabilities, keep in mind even when a probability is very small, it doesn't mean it doesn't matter, right? If there's a small chance of being sick, you might still want to get it checked out if that sickness could cause really bad things for you. That all depends on your utility function, of course. All right, let's stop here for today.